All right. So a post-mix beverage machine is adjusted to release a certain amount of syrup into a chamber where it is mixed with carbonated water. A sample of size 25 beverages was found to have a mean syrup content of X bar is equal to 1.1 and a standard deviation of 0.015. Find a 95% confidence interval. Right? So, right after you read, it's important to find out what distribution you should use. So is it a normal distribution or a T distribution? T. Yeah, this is T, right? Because of two reasons. First of all, the sample size is small, it's 25. And second, because we have the standard deviation of the sample size, not the standard deviation of the population. Right? So that means that we have to use the equations for the T distribution. So N is 15, X bar is 1.1, and S is 0.015, right? So this is the equation from the crib sheet, right? So mu is going to be between X bar minus something and X bar plus the same thing. So the question wants 5% confidence interval, and therefore we have to calculate T of alpha divided by 2, right? So T of alpha divided by 2, and N is 25. So N minus 1 will be 24. So we have to look in the table for T of 0.025 and 24. Right? And that number is 2.06. And we should contrast that number with the normal distribution. So if we had made a mistake and used the normal distribution, then so incorrect solution would be to use the normal distribution. So Z of 0.025 is 1.96, right? So the answer that we would get would be quite similar to the answer here. So based on this, we will get 1.1 minus 1.96 times 0.015 divided by square root of 25. And the other side will be 1.1 plus the same thing. Right? So we see that the interval that we find here, this one, so with this incorrect solution, so with the correct solution, the interval that we find is between 1.09 and 1.1. With the incorrect solution, we actually find a tighter bound, right, a smaller bound, which makes sense because normal distribution always, has thinner tails compared to the T distribution. So note that all of this was incorrect solution at the top. The correct one is the one typed. Any questions? So this basically final answer means that there's a 95% chance that mu is in this interval, right? So remember that 95% chance is for mu, not for X bar, right? So it would be completely incorrect if you write X bar is between these two, right? It's mu that's in between those two. X bar is the number that we have. X bar is 1.1. Any questions? Okay. Okay, let's move on. So the next question is 9-43. A manufacturer produces crankshafts for an automobile engine. The crankshaft wear after 100,000 miles is of interest because it is likely to have an impact on warranty claims. A random sample of 15 shafts is tested and expiry is 2.78. It is known that sigma is 0.9 and the wear is normally distributed. Test the null hypothesis that mu is 3 versus mu is not 3. Right? So basically what happened is that our 15 samples gave us a mean of 2.78, right? And we want to test, let's say the specification sheet says that mu should be 3, right? We collected a sample of size 15 and we found that X bar is actually 2.78. So is mu 3 or not? That's the question, right? So again, it's very important to find out we have to use normal distribution or the t distribution. So which one should, yeah?
I don't mean to interrupt. I'm just curious. When the mean is 2.78 or it's 3, what does that mean in terms of the actual word problem itself?
Say it again, what's the question?
What does X bar mean in terms of the problem? Because it says that crankshaft wear after 100,000 miles. Is that testing to say that there are 15 shafts that have been used for 100,000 miles and seeing if they
Yeah,
have worn?
that's a very good question. I don't understand either, to be honest with you.
All right.
Yeah, because the second sentence doesn't follow the first sentence, right? Yeah, I'm not sure. It's probably something like the question missed something, right? Mu is like mu equal to 3 is probably like I don't know, like a size of somewhere. 3 is probably some critical number in the size of cracks. I'm not sure. Yeah, that's a very good question. And the other question that I have that I don't understand about this question is. The question says 100,000 miles, and in the parentheses it says 0.0001 inch. That I don't understand either. Right? What does that mean, 0.001 inch?
Maybe that's how much it wears after an inch? Or after 100,000 miles, like it wears down by that much?
Yeah, it could be. Yeah, I'm not sure about that either. I don't understand that part either. Any other questions? Okay. So the first thing we have to do, I'm very happy you asked because, we do this because this question is always one of the suggested problems, but the question, is not framed properly. So I fully agree with you. So should we use the normal distribution or the t distribution? Normal, right? Because we have sigma, right? Whenever you have sigma, use the normal distribution, regardless of how many samples you have, right? So the null hypothesis is mu is equal to 3 versus mu is not 3, right? So once we know we have to use normal distribution, we have to calculate z, and z is x bar 2.78 minus mean divided by 0.9 divided by square root of 15, right? So after this point, once we write down what z is, the problem is almost solved. We have to look it up from the table. Did somebody punch this number in? It's okay if you haven't. We just move to the next one. So I think the solution is here. So 2.78 minus 3 divided by 0.9 divided by square root of 15, that's minus 0.95, right? So basically, we can solve this problem in two different ways. The first way we can solve it, we can say that we know the critical range is between, remember that z of 0.025 is 1.96. So we can say that minus 1.96 and plus 1.96. So we know that if we are here, we fail to reject H0, right? And in this case, the Z that we found is minus 0.95, so it's around here, right? I'm sorry, minus, okay. Minus 95, right? So because it's in this range, we fail to reject H0, right? So that means that there's no strong evidence against mu being 3. So that's the first way. Are there any questions about the first approach? Okay, so what is the second approach that we can solve this problem? It's quite similar to the first one, but at the end, instead of comparing, to this range, we can do something else.
Find the p-value?
Exactly. We can find the p-value and see whether the p-value is less than 0.05, right? So with this z that we find, we have to look at the table, right? And we have to find the p-value, right? So I don't think I have the table here, no. So, if you look at this number in the table, this is around, minus 1. So I would think the p-value that we get, is something around, so with z, 0 equal to minus 0.9. Does anybody have the table? No? So with this z, I guess the p-value that we get is going to be, I'm just guessing. So z of 1.96 gives us a p-value of 0.025, right? I'm guessing this will give me, this is very, very close to 0. So I'm guessing this will give me a p-value of like 0.15. Right? 0.17? Wow, so that wasn't a bad guess. Thank you. So 0.17. Right? And this is much more than 0.05, right, that we need. Oh, remember, we have to actually multiply this thing by 2 too, right? Because it's a two-sided test, right? So it's much more than 0.025. The p basically, because half of the 0.05 is 0.025, or 0.17 times 2, which is 0.34, is more than 0.05. And because of this, so this is the p-value. So we fail to reject H0. Yeah.
We multiply by 2 because it's two-sided interval? Or
Yeah.
just internal?
Yeah, so that's a very good question. We multiply by 2 because it's two-sided, right?
Plus 1 we don't.
Yeah, if it was one-sided, then we don't multiply by 2, right? So if the null hypothesis, for example, was mu is less than 3, then we don't multiply by 2, right? We multiply by 2 because we don't know it was, it is always less than 2 or it just happened to be less than 2. That's why we multiply by 2. Any questions? Okay, so let's move on. There's the next part. So let's read the question again. So the next part says, what's the power of the test if the correct mu is 3.25? Right? So basically what's going on here is that this is the correct, we are assuming that the correct mean is 3.25. And the null hypothesis says that mu is 3, right? And we want to find beta, which is the probability of type 2 error, right? So from the table, to find beta, we have to find, the acceptance range first. So let's say that this is the acceptance range. So we find that from the red curve, right? So it's something around 3 plus and minus something. Right? So remember in the previous case, we said mu is equal to 3 versus mu unequal to 3. And for this mu equal to 3, we have a range that we accept mu equal to 3, right? So if this is 3 and we are 3 between something, 3 plus minus something, we say fail to reject, right? So in this part, in part B, the probability that we are interested in is this probability. So probability under the blue curve up to here. This colored area is beta. And we want to calculate beta, right? So whenever you want to calculate beta, the first number, so we have to do like phi of this number, whatever this number is, minus phi of this other number, right? So basically phi of this number minus phi of this number. This number is usually around like -1 or something like that when you calculate the z or the t value. And this number is usually like -4, -5. It's a large number, right? And you can see here, this number is quite far from the mean, right? It's very, very far from the mean. So usually the second term minus phi of something is 0. Right? So let's check that in this question, see whether the second number is 0 or not, or very close to 0. Okay, so for this, remember we have an equation for calculating beta, right? So this is the equation for calculating beta, is z of alpha divided by 2 minus delta. Delta is the difference between true mean and the mean in the null hypothesis. So in this case is 0.25 divided by sigma divided by square root of n, right? So the equation will be z of 0.025. So in this case, delta will be minus 0.25. Is the equation given in the crib sheet like this, or it's does anybody have the crib sheet? because I think in the equation that I gave, it was like delta divided by sigma divided by square root of n, maybe, which is the same thing. You know, I just want to see if it's.
In the crib sheet, it is given the way it is.
Oh, it's. Yeah, so this is from the crib sheet. Okay, all right, thank you. Right, so basically when we check those two numbers, so let me draw that. Sorry. So let me draw that distribution here again. So this is 3.25, or the correct mean, and the numbers that we find are 0.88 and minus 3. So actually one of the numbers is here. So this is very unusual. So the range is actually here. So I draw it with the same color as in the previous slide. So here and here. So this number is minus 3.04. And this number here is 0.88, right? So this 3 is actually transformed to 0. So this is actually, like, this 3 is actually 0, right? When we transform it to the standard form. Right? So when I wrote 3, all I meant was that this is the true distribution. Right? So this is a little bit unusual because, as I showed in the previous slide, usually, you know, this guy appears to be on this side of, you know, on the left side of the true mean. Right? Here is on the right side because the true mean is very close to the null hypothesis. So if I go back, so null hypothesis is 3, the true mean is 3.25, and when we compare to our sigma is quite large, right? Our sigma is 0.9. So these two values are in fact very, very close to each other. So what happened in this question is that this basically, since our sigma is large, then this range is actually something like this instead of what I drew. So this guy is here, and the second one is, you know, somewhere down here. So the area under the curve would be this area. Yeah.
I think I'm getting a little bit mixed up as to which mu is which. So are we saying that? So because you just said, as you were drawing that graph, the true mu that we're testing for is 3.25. So when we're setting up, we would go through. Are we saying that mu naught is equal to 3?
Exactly. Yeah.
Mu is equal to 3.25.
Yeah.
Because
that's the alternative hypothesis. So here, mu A, alternative hypothesis is 3.25.
Okay. Because in the crib sheet, it goes mu minus mu naught. So which one is mu naught?
Yeah. So this is mu naught. Mu naught always corresponds to the null hypothesis H0.
Okay. Can we go to the next slide again?
Sure.
Because in the answer here, let's see, we get that the two of them subtracted from each other gives us a negative number, but I'm not sure. Actually, no, I did the next slide over. Yeah. Okay, so we're doing 3 minus 3.25. Is it not the other way around because 3 represents mu naught?
I see. Yeah, that's a good point. Yeah, because when we gave this equation, we said that delta is positive, right?
Yeah.
And here delta is not positive. So let's check this, right? Let's check this computation. Thank you. So let's check this to make sure that this is correct. So z of alpha divided by 2, that is correct, and that is going to be, so 1.96 plus 0.25 0.25 times square root of 15 divided by 0.9, and then minus phi of minus 1.96 minus 0.25 times square root of 15 divided by 0.9, right? So it looks like this is different from what's written over there, right?
Yeah.
Yeah, it is different. So can somebody please punch this in to a calculator, this one?
The first one is 3.04.
Phi of 3.04.
0.04.
Thank you. And what's the second one?
No, I'm guessing minus 0.2. I don't know.
No, for the other one, oh, you're right, actually. Both of them are the negative of this, right? You're right. Yeah, so this is obviously different from the one here. Yeah, I will have to check. I'm not sure actually.
Isn't it supposed to be a minus?
Which one?
1.96 minus these part of the
Yes,
equation?
thank you. Yeah, thank you. Yeah, so I made a mistake here. So can you calculate this one now? Thank you.
Yeah,
0.88?
88.
0.88. Okay. And this one is still minus 3 point. I guess, yeah, that one is correct because both of these are negative, right? Yeah. Yeah, so my mistake was that here it says negative, but here I put plus, right? So this is weird. Our answer is the same, but the numbers here are different compared to our numbers. Oh, I see what's going on. So I don't know why the type solution here, that's why I made a mistake, because I followed this here and I wrote plus, but the equation here is negative. Right, so the solution, the type solution is correct, but for some reason, instead of this negative, it's written as positive here, the negative is moved here, which is very strange. But at the end, our answers, both answers are correct. So I suggest you follow what we said in class. Delta is always positive, and you use this equation, to avoid any confusion. I'm not sure where basically this equation came from. Any questions? Okay, so to solve the next one, I will quit basically the presentation mode so that we have room to write down. So the third part says what sample size would be required to detect a true mean of 3.75 if we wanted the power to be at least 0.9, right? So when power is 0.9, that means that beta is 0.1 or less than 0.1, right? And here note that the true mean has actually changed. So mu is 3.75 and mu 0 is 3, right? So based on this, we calculate delta. Delta is the difference between these two, and delta is 0.75, right? Delta is the difference between the null hypothesis and the true mean. Right? So delta is 0.71, beta is 0.1. Our goal is to find n. Any questions? Okay. So this is the equation for computing n. It's z of alpha divided by 2 plus z of beta, the whole thing to the power 2 times sigma squared divided by delta to the power 2. Z of alpha divided by 2 is 1.96. Z of beta, which is 0.1, is 1.29. And delta here is 0.75, right? And the sigma was known in the question, was 0.9. So we get 15. We want beta to be at most 0.1. So that means that we have to round this up always. So n is 16. So we need 16 samples. Yep.
I'm a bit confused because they say the power is 0. Or at least 0.9, but we have the beta.
Yeah, so beta is 1 minus power, or power is 1 minus beta, right? So when the question says the power, we want the power to be 0.9, that means beta is 0.1 because power is 1 minus beta. Was that your question?
No.
Okay.
For the B, we search the power 2. Why don't we do 1 minus the...
Say it again.
For the B question, that's what the power of the test.
Oh, yes, yeah. So for the power of the test, we have to calculate 1 minus beta to find the power. We didn't, I thought. Yeah, so you're right. So, yeah, it's a very good point. So in part B, we also have to calculate. So we know beta, therefore power is 1 minus beta, or around 0.2. Yeah, 0.19. Any other questions? So we can compare the results to the previous part, right? So if the true mean was 3.25 with 15 samples, we got a beta of 0.8, a very large beta, right? A very large probability of error. And if the true mean is increased to 3.75 instead of 3.25, with around the same sample size, right? This is 15, this is 15.21. With around the same sample size, we get a much smaller beta of 0.1, right? So in other words, if we draw here, so in the previous case, this is 3.25, and the beta that we computed was this area under the curve, and this beta was 0.89, right? And when we shift the mean to 3.75, right? Beta substantially decreases to 0.1. Right? And that's because this range, right, the range that I colored, so between these two numbers, this is a fixed range, right? This is a fixed, like these two numbers don't change, right? These are like anchors, right? And what we are doing is that we are moving the distribution around. So in this case, we move the distribution to right by 0.5, right? So these two numbers remain the same. Why? Because these two numbers come from H0, and the H0 didn't change, right? So in both of these cases, these two numbers come from H0, which says that, so both of these are around 3. So this is 3, and the middle of these two, again, here is 3, right? So we basically moved the normal distribution to the right, but basically the range didn't change, so this is the same range. And because of that, the area under the curve substantially decreased from 81% to 10%. So this is very important to remember that this range, right, where we calculate beta, always comes from it's around the null hypothesis, which is 3, right? So this range doesn't change with, changing the true value of the mean. Any questions? Okay. So 958, consider the following computer output. We want to test mu is equal to 50 versus mu is more than 50. We have 20 samples, right? And the sample mean is 92, and the sample standard deviation is 0.7. So we want to fill the missing values, meaning that we want to find the standard error of the mean. We want to calculate the 95% confidence interval. Here, since we have 20 samples and we have the sample standard deviation, it follows the student's t distribution, so we can calculate t. And also we can calculate the p-value of testing this null hypothesis. Right? So the standard error, remember that it was defined as standard error of the mean was defined as S divided by square root of n, right? Where S is sample standard deviation and n is the number of samples, right? So this was the definition for standard error of the mean. Okay, so S was 0.7, sorry, and n was 20, so a standard error will be 0.16, right? And t will be x bar, so this is x bar, minus mean, right? Mean was, I guess, 91. If I go back. Yeah, 91, right? So this is mu divided by the standard error. So T0 is going to be 8. So 8 is a very, very large number, right? So for sure we reject the null hypothesis, right? So 8 means that this is 0. It means that we are 8 units away from the mean, right? So we are very, very far from the mean. And, being 8 numbers away from the mean, even for the t distribution, is extremely unlikely. So this 8 intuitively means that we are sampling from a t distribution with a mean of 0, right? So it means that the numbers that we were getting were supposed to be 0, but we got 8, right? So that means that the mean is actually not 0, because 8 is very, very unlikely to get, right? So we don't even need to use the table. But to actually find the p-value, we have to go look at the table for degrees of freedom of 19. And then, as you can see, the p-value falls below the smallest p-value provided in the table, right? So the smallest p-value provided in the table is 0.305. This is even lower than that. So since this value is very small, we reject the null hypothesis that mu is equal to 91, right? So mu is actually, that means that mu is not 91. Now to find the 95% confidence interval, again, we have to use the student's t-distribution. So here, since it's one-sided, if I go back, the question says 95% lower bound. So we want to find the lower bound for the mean, right? So the lower bound would be x bar minus t of 0.05. So remember, since it's lower bound, we don't divide by 2. So it's t of alpha. So t of alpha and 19 is 1.72. So the lower bound that we compute is 92.1, right? So this means that there is 95% chance that mu is actually more than 92.1. That's what it means when we calculate a 95% confidence interval. Any questions? Okay, so we can compare that, to the, like, we can look at the numbers again to make sure everything makes sense. So note that the x bar we computed was 92.3, right? And S is quite small. S is only 0.7, sorry. S is 0.7, right? So the standard deviation is quite small compared to the mean. And remember that the standard error is S divided by square root of n, so we have 20 samples, right? So the standard error will be 0.16, right? So less than 0.2. So when x bar was 92.3 and the standard error is around 0.2, that means that the true mean is around this number, right? And the final answer that we got is actually conforms to that. Here, mu is more than 92.1, x bar is 92.3, right? So a little bit less than. So if we draw all of the numbers here, this is x bar. This is the 95% confidence interval, right? So this is 92.1. So that means that there's a 95% chance confidence interval of mu. So that's the 95% confidence interval of mu, right? So it goes all the way to infinity. And then our null hypothesis was that mu 0 is equal to 91, right? Far, far away from the confidence interval, right? So we can see here also that, we can reject the null hypothesis because this null hypothesis is far from the, confidence interval that we found. Any question? Okay. So, see as the next part. So we found 95% confidence interval, we found T, we found P. So, we basically solved question part A. So in part B, we want to find out whether it's a one-sided or a two-sided test. So it's obviously a one-sided test. And part C changes to if the hypothesis had been mu is equal to 90 versus mu is more than 90. Would your conclusions change? So they wouldn't, right? It's even worse because here it was 91 and we rejected the null hypothesis that mu is 91, right? Now we are even reducing mu to 90, right? So of course we reject the null hypothesis again. The conclusion will not change because this is now even further from the X bar that we found. Right, so the answer to part C would be no, it wouldn't change because it's now even, even for 91, we rejected the null hypothesis. For 90, we are, going to reject it even more certainly. Any questions? Okay, so for 91, the p-value that we found was less than 0.005. Here, the t that we compute is 14, right? The previous part, t was 8, right? Here is 14. It's even further away, right? So even more unlikely. So again, our conclusion doesn't change. We reject the null hypothesis. Any questions? Okay, so let's move on. An article in ASCE Journal of Energy and Engineering describes a study of thermal inertia properties of autoclaved aerated concrete used as a building material. 5 samples of the material were tested. So N is 5. In a structure, and the average temperatures are as follows, right? So this is a very realistic case because it's not giving us mu, it's not giving us sigma, right? We don't have any information about the population. Test the null hypothesis, mu is equal to 22.5 versus mu is not 22.5, using alpha equal to 0.05. And find the p-value, right? So since the question wants the p-value, it's better to calculate the p-value in the first, instead of, rejecting using alpha equal to 0.05, it's better to find the p-value in one shot. So here, should we use the normal distribution or the t-distribution? T-distribution, right? Because we don't have anything. Right, we don't have sigma, and we only have 5 samples, right? So basically, what we have to do is that we have to. So it's a two-sided test, right? So since it's two-sided, we have to calculate t of alpha divided by 2 and n minus 1, right? So alpha divided by 2 because it's two-sided, right? And that is going to be t of 0.025, and n minus 1 would be 4. Right, and our T0 will be, or we have to calculate the mean of those guys. So X bar minus 22.5 divided by sigma divided by square root of 5. Okay, so to calculate X bar, we have to add up all of these numbers, and to calculate, oh, sorry, not sigma. So actually what I wrote is incorrect because we don't have sigma. So this is S, right? Sigma is unknown. And to calculate S, we have to use that equation sigma xi to the power 2 minus sigma xi to the power 2, just divided by n, divided by n minus 1, something like that. Right? So we have to calculate S using this equation. This equation is in the crib sheet, right? And we also have to calculate X bar, which is sigma xi divided by 5. Right? So those numbers are in the next slide. So X bar is 22.49, S is 0.378, N is 5. So T0 is going to be X bar minus mu divided by s divided by square root of n, and that's minus 0.002. So, so from the table, T of alpha divided by 2 and n minus 1 is going to be 2.77, right? So this is 0, this is minus 2.77, and this is 2.77, right? And our T0 is minus 0.002, so this is our T0, right? Because of this, we fail to reject. H0, right? T is very, very small, it's around 0. Any questions? Okay, so we could, I think the question wants the p-value as well. If we go back, yeah, find the p-value, right? Let me see if it's here. Yeah, so I think the p-value for this is going to be 0.5, right? Because the number is so close to the, I don't think actually, I'm sure. This number is almost 0, right? So that means that p-value is almost 0.5 because we are right in the middle, right? That's why it's 0.5. And that's a very large number. That's much, much bigger than 0.05 that we need, 10 times bigger. Any questions? Okay, and we can also see that from the numbers, right? So once we calculate x bar is 22.49, and our null hypothesis was 22.5, right? So this number is almost 22.5. So it makes sense that we don't reject the null hypothesis because x bar is quite close to mu. Okay, so let's move on. So for question 965, parts B and C, B and E are not covered. So only do part B to E, only do part A. So let's now solve a very famous question. It's called Monty Hall problem. How many of you know of this question? Oh, none of you have heard this question? Okay, I'm very happy to hear that because it's one of the most famous problems in probability and statistics, right? And this is a real problem that it was basically, it was a TV show, and the TV show allowed, now how many of you have heard of it? None? Okay, yeah, okay, few. So the question is, there are 3 doors, right? And behind 2 of them is a goat, and behind 1 of them is a car, right? And the contestants don't know which one has a car and which one has a goat, right? So the contestant picks one of the doors. So let's say this is door 1, door 2, and door 3. So let's say the contestant picks door 1, right? So that means picked. And then the other 2 doors, are not picked. So doors 2 and 3 are not picked, right? And then the host shows one of the 2 other doors that are not picked, right? So, if you pick door 1, for example, the host reveals that behind door 2 there was a goat, right? So it shows behind the other doors, it reveals the one that has a goat and doesn't have a car, right? And now you are given a chance to switch. So you can either pick the one that you picked, stay with the one that you picked, or you can switch to the other one, right? Meaning that you can, now you can pick basically door 3. Right. Would you stick with the one you picked before, or would you switch to door 3? So that's the question. And we try to solve this with a conditional probability. So before we try to solve this, how many of you think that, so basically there are basically, I think there are 3 options, right? So option 1 would be to switch to door 3. Option 2 would be to stay with door 1. And option 3 would be doesn't matter what you do. Right? So it doesn't, the probabilities don't change if you switch your door or if you don't switch your door. So is the problem statement clear? Is there anybody who doesn't understand the problem? Okay. So raise your hand if you think that we should pick option 1, which means that you should switch the door. 1. So the question is, if you think that we should switch to door 3, so basically I repeat, let's say we have picked door 1, right? So you pick one of the doors randomly. Let's say you pick door 1, and then the host will reveal one of the other 2 doors that has a goat, right? So in this case, assume that door 2 had a goat. So the host will reveal that door 2 has a goat, and will give you the chance of switching to door 3 or staying with your original pick, right? So if you would switch to door 3, raise your hand if you think that's a better option. 2. And if you think you should stay with your original pick, raise your hand. 2. And if you think it doesn't matter if you switch or, okay, so this one seems to be the winner. It doesn't matter. So I have to say this is a very, very hard problem, right? So when this was published, like somebody, a mathematician solved this problem in a newspaper, and many people, contested with the solution, said that this is incorrect. And I was reading the wiki this morning. Out of those people who wrote to the newspaper and said that the solution in the newspaper is incorrect, 1,000 of them had PhDs, right? So 1,000 people with PhDs said that the solution is incorrect. And there is a famous mathematician, his name is Paul Erdos, right? And he also said that the solution is incorrect, right? So he's a very famous mathematician, and he's one of the most famous people in math. So basically, the reason I'm saying this is that it is a hard problem, right? And the correct solution is that, and which is the solution that was published in the newspaper, is that you should switch, right? It actually does matter, right? So, some people think that it doesn't matter. It doesn't matter. The probabilities don't change. When a door is revealed, it doesn't matter. It doesn't change the probability of the doors, right? Your door might still have the goat or might have, a car. So it doesn't change the probabilities. So many people think that it doesn't matter, right? Like the fact that you reveal one of the doors does not change the probability. So let me try to explain. The reason that I said it's a difficult problem is that if you're unsatisfied with my solution, that's completely okay, that's why, because it's a hard problem. So this is the solution. This is a solution that I like most, right? So at the beginning, before anything is revealed, the probability of you picking the car is 1 divided by 3, right? So this is the probability of picking the car, right? So let's denote that with probability of C, right? And probability of picking the goats is 2/3, right? So I don't think there is any objection to that, right? At the beginning is 1/3 and 2/3, right? So so consider this case instead of the traditional Monty Hall problem. I like to think of let's solve this first, and then I'll try to explain with an extreme case. So let's say you pick door 1. So this one is the pick door. So in this case, the probability of the car being here is 2/3 behind one of the other doors. And so this is the car that you picked. And the probability of the car being here is 1/3. Right? So again, the same question, right? So I just wrote it in a different way. So if you pick door 1, the probability of you picking the car is 1/3. And the probability of the car being behind one of the other 2 doors is 2/3. Right? So when the host, so in the next stage, so this was stage 1, right? At the beginning, when nothing was known. This is stage 2, when you pick one of the doors, right? And now in stage 3, the host reveals one of the 2 other doors. That is a goat, right? So you still pick door number 1. And let's say the host reveals this one as a goat, right? So opens door number 2 and shows that there's a goat, right? Basically, the host will reveal each one of these 2 doors that has a goat, right? For sure, one of them has a goat because there's only one car, right? So the correct answer to this question is that once the goat is revealed, the probability of car being in one of these 2 is still 2/3. So probability of the car being here is 2/3. And probability of the car being here is 1/3. Oops, what I wrote here, what's P of 1/3? So P. So 1/3 is probability of car, right? So the probability of the car being in one of these 2 doors is still 2/3, and the probability of your door being the door with the car is 1/3, right? So what we say here is that, okay, what is the probability of door 3 being a car, given that door 2 was a goat? So if this door is a goat, then probability of this door being a car is still 2/3, right? Because the probability of one of them, should have the car, and this one was a goat, so all of the probability moves to the other door, right? So in other words, the probability of this door having the car is 2/3, and probability of your door having the car is only 1/3. So there's twice higher chance of winning the car if you switch. Right? Yeah.
So even though you have a conditional probability, that wouldn't change, even though you know that door the second door has a goat.
So
It would become like 50-50, which some people would assume.
yeah, so so basically the argument here is that once you reveal that this door has a goat, then what happens is that this probability increases to half, and this probability also increases to half, right? So this means that either this door has the goat or this door has the goat with a probability of 0.5, right? But what I like to argue against that is that when the host reveals the door with the goat in one of these two, he doesn't, I mean, for sure you know that one of these two is a goat, right? So, so basically, the reason I say that is that it doesn't change the probability that, you know, these two, you know, these two have the goat versus this one has the goat. I think in this case it's a bit difficult to argue. Let me give you the extreme case, right, that I wanted to give, right? So suppose instead of the Monty Hall problem, suppose another problem where we have 1,000 doors instead of 3 doors, right? So we have door 1 all the way to door 1,000, right? And let's say that you pick one of the doors and there's one car and 999 goats, right? So for sure, with a very high chance, you're going to pick a goat, right? So let's say that you pick door 1, and then at this stage, we have 999 doors left, right? The probability of the car being here is 999 divided by 1,000, and the probability of the car being here is 1 divided by 1,000, right? So nothing has been revealed so far. All we have done is that we have picked door 1, right? Now, what if the host reveals 998 doors out of these 999 left, right? So this is stage 1. This is stage 2. In stage 3, what the host does is that, so this is door 1, which is the door that we picked, and door 2, door 999, and then door 1,000, right? Let's say the host reveals all of these guys, right? Says that all of these are a goat, right? Because we know that, you know, there's only one car, so only one of these in maximum could be the car if you didn't pick the car already. Would you switch?
So if you follow the same logic as the previous one, picking 1,000 is 99% of chance getting a car, which doesn't make sense.
Yeah, so here, basically, the probability of you having a car is 1 divided by 1,000, and the probability of the remaining door to have the car is 999 divided by 1,000, right? Is that what you said, or?
Yeah, which is like 99%.
Yeah, so in this case, you must switch, right? So the fact that these other doors have been revealed changes the probability of your door having a car, right? It's not 1 divided by 1,000 anymore, right? So I guess in this case, it's a little bit more clear that you have to switch. This is a bit more intuitive, right? So how many of you in this case, right, if you have 1,000 doors and only one of them has a car, you pick one of them, and out of the 999 remaining, the host reveals 998 of them that are goats. How many of you would switch to the other side? So raise your hand if you would switch. Okay, so I see the number increased a little bit from 3 to, I guess, 6. You can think about this problem. It is a very, very hard problem, right? And if you don't agree with my argument, you know, it's completely fine, because, you know, many famous didn't agree. And let me just say that Paul Erdos, the famous mathematician, at the end he agreed when people ran simulations for him, right? So you can actually you can repeat this experiment, you know, 1,000 times, right? Either in real life or computer simulations, right? And those are called Monte Carlo simulations. We use them a lot in my field as well, right? Some, like many problems, are hard to solve, right? Like you can't really calculate the probabilities anymore. And for those problems, you run simulations, right? What that means is that you generate random cases and you count, right? And basically, he was satisfied when people counted that, the probability of winning when you switch is 2/3, is not 50-50 anymore when one of the doors are revealed.
Say that the events are dependent.
What is it? Sorry?
Say here that the events are dependent of picking the door.
So what do you define as your event?
Picking the door that has the car.
Yeah, so basically, if you want to win the car, then it is dependent on which of the doors have been revealed that have the codes. Yes. Yes.
I was gonna ask if they ever revealed, like, not the newspaper, but just anyone in general had some concrete solution. Was there ever like?
So you're saying my solution is not concrete?
I was just wondering if there was any, well, because you said that your solution was
Yeah.
in the newspapers and then several people
Yeah.
did that.
I mean, for these types of problems, unfortunately, all you can do is explain, right? It's sort of like the problem that I said, I mean, that one is easier to prove, that if you flip 2 coins, the probability of getting 2 heads is less than the probability of getting a head and a tail, right? And even I remember for that, some people, weren't happy with my argument. I had to prove and I had to repeat that, and then people became happy. No, this one is even more tricky than that. There's no concrete, yeah. Other questions? Okay, so in the next class, we continue to solve, similar questions. See you guys on Wednesday.